before every use.
Before every use, that's a good one. And that, OSHA requires that every 6 months they go through, how do you want to say this, Robbie? Not a factory test, but a testing center.
Yeah.
Yeah. So they're going to be inflated. They're actually going to be dunked in water to look for leaks, and then they're going to be electrically tested also for insulation. He also said something about, well, what happens if you find a set of rubber gloves or a rubber glove that's got a problem with it? What are you supposed to do with it?
Destroy it.
Destroy it. And usually if we find one out right away, we'd cut some fingers out of it or something like that. Make it, hugely obvious that you had a problem there, so nobody else would use them. Don't just put them back in a bag, or just don't put them back on a truck, because then they have the possibility of somebody else picking them up and using them. Anything else, Mr. V?
Nope, I'm good.
Okay. We'll keep you posted here. Our thought process right now is we might go 2 days online, 2 days straight, Monday, Tuesday. Our field is completely underwater from the recent rains. So we will keep you posted as far as our schedule is concerned. I will agree. I think Professor V will just jump on this also. You guys are moving very well in the overhead part.
Yeah.
So, it's not going to detract anything from you guys to be able to do a couple long lines, and we'll see how the weather's going to be, and 2, see if we can get out of the swamp out there. Okay, so without further ado, you pop open your books. I am on Unit 10 on page 255. And this is talking about alternating current loads. Now, we talked last week of what a load was. What is a load, both either energized or de-energized? What is it referring to? Voltage, power, or current?
Amps either present or not.
Present or non-present. So a load could be on a system or be on your circuit, not yet energized. Okay, so it's not drawing any current or amps, or it can be present and drawing current amps. So that's what they're talking about when they're talking about loads. Now, there are 3 different types of loads. I'll start off in the first paragraph under, I'm on page 255. In a DC circuit, there is one basic type of load, which is resistive. In a DC circuit, volts times amps always equals watts, or true power. This is not true in an alternating current circuit. So let's get some definitions going on here when they talk about different things. And we talk about this chapter. When we talk about current loads that are on a circuit in the book, and as far as the industry is concerned, they're talking about the actual load itself, not what it takes to get volts and amps to that load, because that's going to make you're going to have capacitance, you're going to have resistance, you're going to have inductance on every circuit that you have. But when they talk about loads here in the book, they're talking about the actual load that's attached, a light bulb, a motor, a stove element, and such. So I've moved over to 256. Circuits can have 3 different types of loads. I want to note this down: resistive, inductive, and capacitive. Each of these loads produces a different circuit condition. In this unit, we will be shown that volts times amps may not always equal watts in an AC circuit. The first one, resistive loads contain pure resistance. Now, like I said before, just a couple moments ago, the load itself on a resistive load is pure resistance. Examples include electric heating equipment. So the old-timey stovetop that had the ring and the element that would heat up, that's a resistive load. The element that's in your water heater, that's a resistive load. Or the element that's in your dryer, that's a resistive load. I think one of the most common is the filament light bulb. The filament itself is a resistive load. Now, what are the characteristics of each? They produce heat the current and voltage are in phase with each other. We'll talk about that in just one moment. Only the resistive part of the AC circuit can produce true power or watts. Okay, so what are we talking about? I'll bring up hold on one second. So I'm going to share a paint screen. All right, that's there. 4. Share screen. Okay, you guys see that okay?
Yep.
Thank you very much, Professor V. All right, size, we'll go up to this size. So what they're talking about here in this resistive load section, I'm going to have an AC voltage output going down the circuit, and my all but famous light bulb drawing here, and then a path to ground, and the filament that's inside. So only the resistive part of an AC circuit. Do I have a complete AC circuit drawn up here?
Yeah.
I do. Okay. It can produce true power or watts. So what you do not take into account is whatever is supplying it, how I'm getting the voltage to the circuit, and such. Only the element that's inside is what they call true power, or the part that you're taking measurements on as far as a resistive load. Only the element itself. Okay, there are other factors going on in all the other parts, and we know conductor, does it have impedance on it? Is there impedance on the conductor that's going to my light bulb?
No.
I heard a no out there. Is every single conductor out there a perfect conductor?
No, it has impedance.
So all conductor has impedance. So there's the resistive. There's more resistance in your circuit. I'm talking circuit now, not the load. Okay. Does it give off a magnetic field when current flows through it?
Yes.
Okay, so there's the inductive. We'll get to that definition later. So that's why they're stating in the book the true part of it is just the filament itself. There are other factors going on in the complete circuit that affect it. All right, so I'm going to move down to the figure at the bottom of page 256. Sorry about that. Let's see. And I'll draw the sine wave diagram that they've got out there. All right, so the top line is voltage. Then the next line just below that. I'm doing pretty good here today.
Yeah.
Is current. So when they say that a true, and remember, this is just the filament itself, when they say they have a pure resistive load, the volts and current are in phase. Now, what do I mean by in phase? Not the phase conductor wires we've been talking about. Now we're talking about the sine waves. Anybody got by the picture that they see here, got a definition of what they mean by in phase?
Working
They
together.
rise and fall at the same rate.
Rise and fall at the same rate or working together. I mean, those both are good definitions. The peak of volts and the current amps that it's been drawn by the load are right at the same moment in time. To be totally honest with you, on our electrical system, any kind of electrical network we have, either a power company or electronics in a building or the electricity that flows in the building, this is our perfect condition. Remember, we got other factors going on here. This is perfect condition for the utility. Okay. Whenever they're producing volts and the current demand is here in the circuit, it's at its peak. Remember, when I raise my volts, what happens to my current?
Goes
Voltage
down.
raised, current lowers, and you'll notice the current line is where below the volts. It's not above it. We definitely don't want that type of situation. So I'm producing power at my best, and current's being drawn when my power is at its, when my current's at its best. Perfect condition for our utility. Okay, so it keeps this current line below what's going on. So what are the attributes of some of the, with resistive loads? One, they produce heat. All right. Another one that's good to put out there too, produce light and heat. Okay, resistive loads. The current and voltage are in phase. That's number two, and we just discussed that with each other. And only the resistive part of the AC circuit can produce true power. So that when they take their measurement of Ohm's law, they're doing this point right here. Peak of the volts, peak of the amps. And that is true power. Any questions about resistive loads? Now, obviously, these waveforms that you're seeing right here, is this going on an electric utility circuit perfect like this?
No.
No, I mean, there's just no way. There's just too many factors out on an electrical circuit, especially utility network, either transmission or distribution, that this is never going to be happening at the same time. And to be, let me go right here, file, new, don't save. I'll draw these sine waves again. Volts. I'm just going to draw this one out of phase a little bit. Okay, so we're going to put volts and current right here. These lines are moving back and forth all the time. Back and forth. Because certain things are happening to our circuit. So we might have an instance where the amps are ahead. We call that leading. And we might have a condition where the amps are behind, lagging. We can also flip that and we say, well, the voltage now is lagging and the current is leading. What do I mean? What do I mean by that? The voltage is behind. In this instance right here, it's lagging. And the amps line is leading. It's ahead. All right. So these lines, are moving back and forth, and it's so, well, it's 60 times per second, that these are happening back and forth so often that you can never have them truly in a pure resistive circuit. It's just not conceivable out there in the world. What you do want to do, as far as your circuit is concerned, is try to keep these as close together as possible. I'll do the bottom line. And there are ways that you can do it on a circuit. The closer you keep them together, the more effective your circuit is going to be as far as providing true power. Any questions there? None heard. We'll continue on. All right, so anytime that a circuit contains resistance, heat will be produced. Well, let's think of some things. You touch your hand to a filament light bulb, it's hot, all right? Stoves are hot. Water heater, that thing's making hot. When you put your hand to a motor that's running, is it hot?
Mm-hmm.
Yeah, okay. So there's going to be a little bit of resistance inside a motor. When an AC voltage is applied to a resistor, and I like to call that resistance, The current flow through the resistor will be a copy of the voltage, and you can see that in the figure that you have below. The current will rise and fall at the same rate as the voltage will reverse the direction of flow when the voltage reverses polarity. In this condition, the current is said to be in phase. You guys are gonna have to know that word, in phase. And like I said, cannot happen all the time. We want to try to keep voltage and current as close to phase as possible. But when they're talking about this resistive load, they're talking about the filament in the light bulb itself, not the entire circuit. True power, I'm on the top of page 257. True power or watts can be produced only when both current and voltage are either positive or negative. What do they mean by that?
Above or below the sine wave?
Above or below, that's close enough to get a good description that's going on right here. And remember, they've got that word in front of power. True power means they're taking their measurement right here at the peak, and they're taking their measurement right here at the peak. Obviously, if my voltage and current are not in phase, which this one is not, I can't measure true power because they're out of phase. And the same thing that you said, Scott, measurement is taken right here. Okay, it's got to be at the peaks of both the voltage and the current. Okay, so that's a resistive load. Let me take a look at the quiz and make sure I'm giving you guys a good description of what that's about. Characteristics. All right, that's fine. All right, let's move on. We'll go to inductance here, and then we'll take a break. So I'm in the middle of page 257, inductance. Inductance is one of the primary types of loads in alternating current circuits. Some amount of inductance is present in all alternating current circuits because of the continually changing magnetic field. Remember that first diagram I put out there when I put the AC, then the line, then the light bulb? I put current on that conductor. A magnetic field is going to be introduced. And once I start creating a magnetic field, that's inductance. Okay. The amount of inductance of a single conductor is extremely small, but it's still present, and in most instances is not considered in circuit calculations. Circuits are generally considered to contain inductance when any type of load that contains a coil. All right, you might want to mark that, underline it, what you need to do in the book. Any type of load that contains a coil is used. Loads such as, here's some of the definitions of some of them. Motors. What do we use on our electrical power system? What do we use in a utility? It's vital to have transformers, lighting ballasts, and chokes all contain coils of wire. All right, it's kind of throwing you off here. If you look down at the bottom, it's figure 10-2 is power in a pure resistive circuit. That probably should have been different. I'm going to show you a different one here in just a moment. So know the attributes of an inductive load. An electric motor, perfect example. Right? Transformers, perfect example out there of an inductive load. Think of it. Between our primary and secondary coils of a transformer, is there actually any solid type of electrical connection? Let me draw this up here. So here's my primary coil. Here's my secondary coil coming down here. Is there a physical connection between the primary and the secondary coil?
No.
Piece of wire? No. Right? I create a magnetic field here, and it induces a magnetic field onto this one, induced induction. All right. How about in a motor? So I got coils on the outside of my motor here. Then I've got my motor shaft right here. Then I got another set of coils on the inside of the shaft. Is there any connection between the outside coils and the inside coils?
No.
No, there can't be. Otherwise, it wouldn't turn, right? You wouldn't be able to spin it. So electromagnetic fields are coming off here, making the motor spin. That's the attribute of an inductive load. No physical contact between the two. What do they mean in the book by a ballast? Does anybody know what a ballast is? In a light?
It's like the filament in a bulb, and or the ends where you stick the bulb up in.
Right. Well, you're talking about like in a fluorescent light, right?
Yeah, like where you stick the little connections into on each side.
Yeah. A ballast in itself is a momentary high voltage transformer. That means, when I mean that, it for a moment in time until the gases inside a fluorescent light bulb light up, it's going to produce a high voltage until that light does light, and then that voltage is going to go back down to normal voltages like 120 or 240. But in order to do that, here's the vital part. What has coils in them? Transformers. So that's why it's included as an inductive load. All right, so I'm going to move over to page let's see. I'm in the middle of page 258. In Unit 4, we discussed that whenever current flows through a coil of wire, a magnetic field is created around the wire. If the amount of current decreases, the magnetic field will collapse. It will also decrease. Several facts concerning inductance are as follows. When magnetic lines of flux cut through a coil, a voltage is introduced in the coil. So we've got voltage, current, and movement. And then when we have those three components right there, we're able to produce voltage on the other coil. And induced voltage is always opposite in polarity to the applied voltage. We'll get in that in just a moment. The amount of induced voltage is proportional to the rate of change of current. So and that goes right back. That's a simple facts right there. Again, raise my voltage, lower my amps, right? Lower my amps, my voltage raise. An inductor opposes the change of current. Okay, so look at the figure on page 259. 10.6. The applied voltage and induced voltage are what? 180 degrees out of phase with each other. Okay, so let me go back to my screen right here. New. Don't save. I'm going to draw them both, what we've done so far. Okay, what kind of circuit is this? Resistive, inductive, or capacitive?
Resistive.
Perfect. Ooh, that line's squiggly. What kind of circuit is this?
Induced.
Inductive. Correct.
Inductive.
Right. All right. The applied voltage and the voltage present are, this is in phase. Inductive is 180 degrees out of phase. Where do we want to try to keep our circuit? Resistive. And remember, as soon as we install an inductive load, they're talking about the inductive component, the actual transformer itself, or the actual motor itself, not the circuit that feeds it. Is this good for our electrical utility system? This
No.
one's perfect, right?
Yes. No.
This is what we want all the time. When I produce voltage and amperage, when I'm feeding that out of my power plant, this is the way I want it to be. Optimum. What about this one? Inductive.
No.
No. All right. It's gross. That's exactly what we don't want to happen. And there are ways to alleviate it. We'll get to that in a little bit. All right. So in phase, 100, and an inductive load is 100 degrees out of phase. All right. See what time we got here.
About 9:30.
Showing 9:40. Let's take about 10, and we'll be back about 9:50. Okay. Take a break, guys. Okay, so thus far we've discussed, and I've given, so far we've talked about these things. We talked about it in their pure states. All right, now I'm going to move forward in the book a little bit because I like these diagrams that you're looking at in the book. Now I moved up to page 264. Now when you see these diagrams that they're showing of the sine waves, they're more applicable. And remember, there's constant movement between the voltage and current, induced voltage, and the circuit current that's on the circuit. Those are constantly moving, but they more represent what's happening on an electrical network or utility system. Either the voltage is lagging or leading the current, or the current is lagging the voltage. They're vice versa, and we'll discuss that again here in just a moment. So if you look at the figure 10-12, top of page 264, induced voltage is proportional to the rate of the change of current. So if my current goes up, right, my voltage is going down, and you'll notice that in the figure. That's because the voltage and current are not in phase. So the current is rising, and the voltage line is a little bit lower than the current line. And the same in figure 10-13, right? The circuit current is lower, but the voltage is what? Higher. So when I raise my voltage, my current lowers. Now that when they're talking on these diagrams right here, they're talking because these are now circuit wide. They're not talking pure anymore, like you're seeing in the figure I've got drawn up there. So on my circuit, I've got some resistive, and I've got some capacitive, and I've got some inductive equipment attached to it. So those more represent what's going on there as far as the whole circuit is concerned. Same with the figure for 10-14 on the top of page 265. The circuit lags the voltage by 90 degrees. Okay. This definition you will have to know for the quiz. And read this, when you see this on the quiz, read this closely. So I'm going to draw one circuit line with both sine waves. That's my voltage line. Will come from here, go into here. And that's my current line. I'm just going to draw amps, volts. Now, however the question is worded is what you got to look out for. In this situation, I've got two things that are happening here. And it just goes by what the question is asking for. All right, is the amps line leading or lagging? Is the amps wave leading or lagging volts? It's leading. Now I can flip that question right around. Depends how I word it. Is the voltage in this circuit lagging or leading?
Lagging.
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 Okay. Watch, right. So if you see a question that comes out here, why don't we just go ahead and do it? Okay, I'm just gonna leave it just the way you said. Watching the questions, all right? Just watch the question of how it's worded. You have two instances here. Amps is leading and volts is lagging. Just watch out what I'll ask in the question. The sine wave that I provided, is the volts leading or lagging? Lagging. Is the amps leading or lagging? Leading. You got to find the correct line. Sorry about that. The correct line to answer the question with. The correct sine wave. Any questions there? Fantastic. All right, so I'm going to move up to page and get to the last one we need to know here. File, new, don't save. So we've talked resistive. And we know the properties of resistive, right? And what types of loads are attached to that to make it resistive. They give off heat, they give off light. We've talked about inductive. Okay, no physical contact. We know what the sine wave looks like for it. And inductive includes motors, ballasts, chokes, and transformers especially. All right, we're going to talk about capacitive, and that's our third. Okay, so I'm going to draw the inductive load on this line. And remember, when we talk in these first instances here, we're talking about pure. What did an inductive load look like? Volts and required amps. Volts and required amps, okay? And that is not good on our system. But it occurs. How many transformers do you think are attached to a electric circuit? Hundreds, maybe thousands. So it's definitely happened in our circuit. A capacitive wave is, guess what? And watch what I do with the letters right here. What's the difference in a capacitive circuit?
They peak at the same time.
Volts are in the negative.
There you go. Okay. It's 180 degrees or completely opposite an inductive circuit. We'll talk more of that in just a moment. Okay. Capacitive loads. Now, remember, this book is made for electricians. It's not made for utility. So we'll introduce why we have capacitive loads, or what the capacitive loads are on a transmission or distribution circuit. Capacitive loads are the third type of loads that can be encountered in an alternating current circuit. Capacitive loads are the exact opposite of inductive loads. Inductors oppose a change of current, and capacitors oppose a change of voltage. In a pure inductive circuit, the current lags the applied voltage by 90 degrees. In a pure capacitive circuit, the current leads the applied voltage by 90 degrees. Inductors store electrical energy in the form of electromagnetic field. Remember, electromagnetic inductance, and then return it to the circuit. Capacitors store electrical energy in the form of electrostatic. So now we're talking voltage. One's current, that makes induction, magnetic field, that is induced. Capacitors are the complete opposite of that. They store energy in the electrostatic form, which is voltage. To better understand how a capacitor works, it will first be necessary to discuss what capacitor is. Now, I'm just going to read you this. It applies to the electrical industry too. Capacitors, caution. It is the habit of some people to charge a capacitor to high voltage and then hand it to another person. While sometimes people think this is comical, it is extremely dangerous practice. Capacitors have the ability to supply an almost infinite amount of current. Okay. Under some conditions, a capacitor can have enough energy to cause a person's heart to go into fibrillation. I can guarantee you, gentlemen, once you start working with capacitors at voltages of 7,200, 12,470, or 34,500, they will kill you. All right, this is talking to electricians. We're talking about electrical industry, and we'll talk of how to prevent that later on. All right, so we're going to move. I've heard some people say this, well, or ask this: is a capacitor a battery?
No,
Why not? Give me reasons why.
it has to be. I don't know.
You
I
know,
thought that it would have to be like,
all right. I mean, in essence, right here, what a capacitor does in a capacitor bank, or a capacitor as far as how it charges and discharges, is during a point in time, a capacitor is going to take and it's going to charge a plate at what times? You see, I've got these areas right here checked. Right at the peak of the volts, or the negative side of the volts, right when that happens. Okay, when that moment happens, it reintroduces voltage back into the circuit. Only here. Okay, so it's actually, if you want to put it this way, boosting the voltage. How many times per second does it do that?
60.
60 times per second. Anybody else can answer other than Scott? We know that the 60 signal is 60 times per second. So it's reintroducing, it's giving off an electrostatic charge right back into the circuit. That's actually not really a battery because it's happening so fast, but it's actually give your volts a boost. And when you boost your volts, what happens to your current? It drops. We're right back to that same definition again. Okay. So I'm going to show you a couple pictures here, and this is going to be in some of your questions. Hold on, I'll stop this share. Let's start another one. So in order, and what kind of circuit waveform do we want to have in our circuit? Resistive, inductive, or capacitive?
Resistive.
Resistive, okay. We want resistive all the time, and it is best for our production down there at the generating plant. Right? When my volts are high, my amps are lower, and that's helping my entire system. Now, if we got completely inductive on our circuit, what do you think when we lower our volts and our amps raises? Well, what do you think it does with our conductors? Amps is raising.
Worse.
Yeah, it's going to make it worse. I mean, it's going to get to the point where you've got so much inductance on there, your circuit cable and conductors are not going to be able to handle all that extra current. So we definitely want it to have our system be resistive. All right, let me move this over here. Watch a short video, maybe. All right. Share. Let's go to YouTube. Share. Let me know when you can see that.
Got it.
Hold on.
Don't got it.
I know. I changed it so you can hear the sound better.
Yeah.
That's the wrong one again, isn't it?
Yep.
Sorry, gentlemen. It's Monday. Share this. Share computer. Sound. Share. Okay, here we go. Got it?
Yep.
All right, here we go.
The nature of electrical load, we can classify them into three types. In this video, you will understand these three types of electrical load in detail. Also, In the end of this video, I will talk about one of the very common misconception about a particular type of load. So to understand the types of electrical load, you need to watch the video. Hello and welcome back on my channel. My name is Gaurav J. I post videos related to electrical engineering with easiest explanation on this channel. So if you're interested in learning electrical engineering in easiest way, make sure you click on the subscribe button and the bell icon. Before you understand the different types of electrical load, it is important that you understand the three different powers, that is active power, reactive power and apparent power. And hence I'll recommend you to watch my video on that first, the link for which is given in the description of this video. Understand those power and then come back here, as that will make things even more easy to understand. Already done watching that video? Then let's start. First, let's understand what is electrical load. In the easiest language, anything that consumes electrical power is called as electrical load. So that includes light bulb, computers, refrigerator, etc. All these consumes electric power and hence we can refer them as electric load. Now if we look at the nature of such load, we can actually categorize them in three different types, and those are resistive load, inductive load and capacitive load. In this video, I'm going to talk about these three loads. Now there can be other types also. For example, if you are working in a power distribution company, you can say we also have industrial load, residential load, commercial load, etc. We are not going to talk about those load in this video. We are only going to talk about the basics, that is resistive, inductive and capacitive loads. Let's first.
Homeowners, this incredible tip
my
is
goodness.
just for you. If you owe less than $331,700.
Let's understand the resistive load. Load which consumes only active power is called as a resistive load. And if you look at the voltage and current waveforms of such load, you will find that the voltage and current are perfectly in phase with each other. Now, when I say they are perfectly in phase, that means both the waveforms reaches their peak value at the same time. They also reaches the zero value at the same time. One example you can see on your screen. As such type of load only consumes active power, power flows from source to load only. So for instance, this is the AC source connected to a resistive load. Now in this case, power will only flow from source G to load L. There will be no power flowing from load to source. Yes, in few cases power also flows from load to source, which I have explained in my active, reactive and apparent power video. As such loads only consumes active power, power factor of such loads is unity, and which is a very good sign. If you want to know more about power factor.
Okay, so when he's given another definition here, and that we get later onto this when we talk about electrical power systems. When the generating source, or the one that's giving electricity to a resistive load, we called it what? That waveform was what? In phase, correct? Right, it's in phase. Now the industry and engineering also terms that as what they call a unity power factor. All right, both the load and the generation source or the voltage source are in unity. So just remember that for the future.
In detail, you can watch my complete playlist on that, link for which you will find in the description of this video. Now let's look at the examples of resistive load. Lights, heaters or any other load that consists of only heating element, those are the examples of resistive load. Let's see what are the properties of resistive load. These loads consumes only active power. Voltage and current waveform of such loads are perfectly in phase with each other. Power factor of such load is unity. Power always flow from source to load. You can take screenshot of this slide for your quick reference.
Karen, man, come on in. Watch your head, man.
This is why you're always at my house.
Oh, I downsized my lifestyle.
Now let's understand inductive load. Load which consumes only reactive power is called as inductive load. And if you look at the voltage and current waveform of such load, you will find that the voltage and current are out of phase with each other by 90 degree. Now when I say they are out of phase, that means both the waveforms reaches their peak value at different times. They also reaches the zero value at different times. One example you can see on your screen. If you look at the waveform, you will find that voltage has head start than the current. We can also say current is lagging behind the voltage. As such type of load only consumes reactive power. Power can flow from source to load or even load to source. Further, power factor of such loads is not unity. Power factor of such loads is lagging in nature. Let's see few examples of inductive load. Electric motor, fans, washing machines, or anything that has a motor inside it. Also, reactors used in power system is an example of inductive load. If you know few more examples of inductive load, do let us know via comments. Let's see what are the properties of inductive load. These loads consumes only reactive power. Voltage and current waveform of such loads are out of phase with each other by 90 degree. Power factor of such load is lagging. Power flows from source to load and load to source. You can take screenshot of this slide for your quick reference. This type of loads are not easy loads as the resistive loads. They create a lot of problem in the system, but of course they are equally important. Since current lags behind the voltage by 90 degree in such type of loads, that makes switching of such load difficult. As we know, circuit breaker opens at current zero condition. If you look at the current and voltage waveform of such load, you will find that when current is zero, voltage is maximum. And hence when circuit breaker opens at current zero, voltage across the breaker contacts is maximum. Whereas in case of resistive load, both current and voltage become zero at the same time. Therefore, switching such type of inductive load is one of the critical operation. Such type of load also affects the power factor of system heavily, and hence electricity bill goes up.
What's the difference between your lawn and a true green lawn?
Okay, so what was his last comment right there? Anybody catch that?
The electric bill go up.
Yeah. Oh, well, why is your electric bill going to go up when you have a lot of inductive load? Say, we'll just give the example of your house. First, do you have any motor load that's in your house?
Yes.
Give me some examples there, Trevon.
Washing machine.
Washing machine. Okay, what else?
Dishwasher,
Dishwasher's got a motor in it. What's heating and cooling your house?
air conditioning,
AC
Right, both the
unit.
motor in the unit and the condenser outside, if you're using an outside unit, your refrigerator. So there is a good bit of motor load that's in your house. Once that gets really high in inductance, your voltage is high, your voltage is low and your current is high. Well, is that going to make your meter spin faster?
Yep.
Okay. So before we go on with the video, who's ever worked, anybody do any air conditioning work? None there? All right. Out of all those motors that we're talking about there, inside a residence, what do you think is the one that's the most, gives the highest amount of load in your home? What do you think is the one that's working the hardest?
the AC.
The air conditioner. Okay. Air conditioners. Now, back in the old days, they don't have this, but now in the new, they have what they call a startup capacitor built right into the unit. So there's actually capacitance built right into an air conditioning unit that's going to help to offset what?
The inductive load.
The inductive load of an air conditioner. They're built with them right now. If you live in a home and your outside unit fires up and your lights go real dim for a moment, that startup capacitor is not doing its job. If that thing starts up and your lights in your house don't dim, then you know that startup capacitor is doing a good job for you. All right.
Capacitive load is similar to that of inductive load. In capacitive loads also, current and voltage are out of phase with each other. The only difference is that in capacitive load, current leads the voltage by 90 degree, whereas in inductive load, current lags behind the voltage by 90 degree. Now let's talk about the misconception on which I spoke in the beginning of this video. Basically, capacitive load do not exist in standalone format. Capacitor banks are installed to improve the power factor of a load or system. Their job is to supply the reactive power. Therefore, we cannot call capacitor banks as capacitive load, because load is something that absorbs the power. I have seen in many places on the internet, people are calling capacitor bank as capacitive load. Well, I think capacitor bank supplies reactive power and hence it cannot be classified as capacitive load. For instance, let's say I have a 230 volt AC generator and a capacitor bank connected to it. Reactance of capacitor bank is 23 ohms. Therefore, the current drawn by the system would be, let's say, 10 ampere.
Okay, he gets into a lot of technical data and he goes off on a spin here as far as what he calls capacitive loads that are on a circuit. And the electric utility, I'm glad he showed the electric utility one. We do, as far as terminology is concerned, now he can go through all the electrical schematics he wants to. We do consider them a capacitive load. They do have a purpose on an electric utility circuit. So let me close this down. I'm going to go to Google Maps here real quick. Maybe. There we go. Maps. And we're going to run over to the college here real quick. All right, let's minus out, get a little bit further out there. So while we're driving over to the college here, and thinking about the building itself and what feeds into the building, do you think, what kind of loads do you think are at Horry Georgetown Tech, the college itself? Take a guess.
Resistive? I'd say resistive.
All right, what kind of lighting do they have out there in the inside the classrooms? It's fluorescent. So what do you think's used to start those up? A lot of what?
Voltage.
Resistive, capacitive, or inductive?
Capacitive. Capacitive.
Okay. Let's state this again. What's inside a fluorescent light, which every classroom and every hallway has a fluorescent light in it?
A filament?
Nope. All right, fluorescent lights do not have filaments in them. It's all gas. What do I need to do to that gas to make it ignite? What do I use?
Inductance.
Right, I use a ballast. Okay, so that's a lot of inductive load. What else? What keeps the buildings hot and cold?
Furnace.
A what?
AC unit.
AC units, and a ton of them at that, okay? A lot of inductive load is happening out of the college. So let's get down here. We'll zoom in. So we have determined, and two is, there's a lot of transformers out here too. A lot of three-phase transformers are at this location. That's inductive load. On top of the buildings, we have a lot of air conditioning units. You can see them speckled all over the campus here. All right, all of these, that's building 300. That's an AC unit. So we've pretty much determined there's a lot of inductive load out there at the college, correct?
Yes.
Okay, good. So what do we do? Now, is this inductive load that's here close to the college, is it good for the electrical power system, our electrical network? Do we want inductive loads?
No.
No. So how do we take care of inductive loads? What do we use to offset the inductive load?
Capacitors.
All right, fantastic, fantastic. Good answer right there. So located very close to the college In fact, right in front of it, guess what we have? A bank of capacitors. Okay, so this helps our circuit as far as offsetting the amount of inductive load. Important to note here, how far away is the capacitor bank or the capacitive load from the college? It's right there at it. Yeah, it's really close to it. So you're going to want to, as far as your electrical network in your distribution system, you want to have the capacitive load or the capacitor bank as close to the inductive load as possible. All right, it's just more effective in that case. Can you move it down the highway 5 or 6 fans? Yes, you can. All right, but it's more effective and offsets that inductive load better when it's closer to the inductive load itself. Okay, any questions there? Now, as far as the electrical industry, this is the only reason why we use capacitance. We use capacitance on our circuitry to offset inductive loads. All right, you will see, and I'll show you this one. If it's on the transmission side, if they have a circuit or a circuit wide of transmission that has a high amount of inductive load, think of it in this case, who feeds Georgetown Steel? What company?
This is Sammy Cooper.
It is, buddy. It is. All right. So what? In order to heat that steel up, what they're going to use in there, as far as that plant is concerned, is inductive heaters. It's the most efficient. They're not using fires. They don't have smokestack. They're using an electricity. I know you've heard of an inductive stove to make heat, and that enough heat, high enough, to be able to melt steel and form steel. Well, what do you think that's doing to the electrical transmission system? Not what we want. Transmission feeds into Georgetown Steel, not distribution. So what do we put at our transmission substations? Take a look at that picture. Huge, huge banks of capacitors. This is there's one. Each one of these stacks is for each phase. So one phase of transmission has that much capacitance on it to offset all the inductive load that's on that circuit. Make sense? Mm-hmm. Oh, I heard somebody say, mm-hmm. Okay. So what time are we holding here?
10:22.
Dang, time be flying. All right, let's go 10:35. All right, let's take a break and we'll be back. Okay, so we'll get started back. Okay, that should take care of what we're talking about as far as resistive, inductive, and capacitive loads. Those will be on the quiz. So coming up next on the book here, I'm in Unit 12, and we're going to go ahead and start into three-phase circuitry. And I'm on page 300. Most of the electrical power generated, and do take that into consideration there, generated power in the world today is three-phase. Three-phase power was first conceived by Nikola Tesla. In the early days of electric power generation, Tesla not only led the battle concerning whether the nation should be provided with low voltage direct current or high voltage alternating current, but he also proved that three-phase power was the most efficient way that electricity could be produced, transmitted, and consumed. That's obvious. If we have three-phase power, or we generate an AC alternating current, we're able to transform it. DC, we are not. We've discussed that before. Three-phase circuits. There are several reasons why three-phase power is superior to single-phase power. All right, these are important, come up on the quiz. Numbers 1, 2, and 3. The horsepower rating of three-phase motor and the kVA, kilovolt amp rating of three-phase transformers is about 150% greater than for single-phase motors or transformers with similar frame size. So I'm actually, if I was to have a 100 horsepower motor running on single phase, right, I could actually raise that rating of that horsepower 50% more if I went to three-phase. So when I introduce three-phase motors, I'm actually able to power more motor with the same amount of power that I'm providing at three-phase rather than single-phase. 2, the power delivered by a single-phase system pulsates. We've seen that in the AC sine wave. The power falls to 0 3 times each cycle. We've answered that question before. The power delivered by three-phase circuit pulsates also, but it never falls to 0, right? Figure 12-2 of the book, and you've seen it in when I had that electrical generator and the sine waves are moving, the three-phase one, and the sine waves are moving. At any point in time, did we not have voltage? Was voltage present all the time? At least one of the three phases, were they producing voltage? Yes or no?
Yes.
Yes, okay, at least one. Sometimes two. Only one of the three phases was at 0. The other two are still producing voltage. So you have voltage present all the time. Whereas in a single phase, each sine wave, you're at 0 3 times per cycle. 3, in a balanced three-phase system, the conductors need be only about 75% of the size of conductors for single phase. So if I'm using three-phase conductors, both of my primary or secondaries, I can actually reduce the size of those by 25% if I was to run it in single phase. Once again, that attributes right back to, now that I'm providing voltage all the time in three-phase, I raise my voltage. What happens to my amperage? It lowers. Right, so now I can use a smaller conductor. A single-phase alternating voltage can be produced by rotating a magnetic field through the conductors of a stationary coil, as shown in figure 12-3. We've seen this before. Okay. So I've moved over to page 302. There are two different types of three-phase that are produced, and it's dependent on how you want to use those. What did I do with, there it is. So I'm going to go to a share screen. I lost my book. And I'm going to share, wow, I've got all those screens up. Screen 2. Share. Okay, Professor V, let me know when you got that.
You are on, yep.
Let me get back to my correct page. I'm on page 302. I'm at the bottom of the page.
Yep.
The first three-phase type of connection is what they call the Y connection. I'll draw that connection drawing here. Now, big thing here, why do you think they call it the Y connection? It looks like a Y. All right, each one of these represents a coil or transformer. So you got to include these squiggly lines in here to make the Y connection. And each end represents a phase. So I've got A phase, B phase, and C phase. Now you'll see this in some drawings and some not. I like to include it all the time. What do we have to have for current to flow? When I did my drawings, when I did a single line, I came off an electric source and I did my light bulb, came down here and went down. What did we call that? The full distance here?
Circuit.
It's a circuit complete path. All right, I've got to have a complete path in order for me to energize this entire circuit and for current to flow. Remember the switches? Won't do those all over again. Anywhere I put a switch in this circuit, I've cut off my complete path. I don't have current flow. So in the Y circuit, I come off here, and guess what? Do I now have a complete path? That's grounded at the middle.
Yes.
Yes.
Yeah.
So now I have a complete path. Now current's able to flow. That is the Y three-phase configuration. Okay. A wire star connection. Let's go over here. I'm going to move, and we're going to come back to this. This is more later on, but this is only the part that you need to know for the quiz so far. The next one is called what they call the delta connection. And it's shaped just like what? Delta. All right, once again, each one of these represents a phase, A, B, and C. Do I have a complete path? I have not, what have I not included that I included in this one?
Ground.
Ground.
Right, but do I still have a complete path?
Yes.
You do, okay? All right. What a delta connection does is, as far as current flow, is it relies on being out of phase. Remember, it relies on the difference in potential between one phase and another. I'll draw my straight line here. And I know this is not quite that. It relies on the difference in potential from C to B and B to A. That's a delta connection, but it still does complete a full circuit between all three phases. Let's just discuss this for a moment. In the transmission line pictures that we have seen, you've got three transmission lines. What is it missing? Which line is it missing? Transmission. Now rephrase the question. Does transmission have a neutral?
No, it doesn't.
No, it doesn't. All right. Does my delta drawing have a neutral?
No.
All right. How about distribution? Does distribution have a neutral?
Yes.
Yes. Okay. So you're able to differentiate right away. Y is used in distribution. Delta is used in transmission. Okay. Robbie, keep me square on the questions here.
All right.
Power is available in three-phase and both motor and balanced three-phase systems of conductors. The Y diagram is in, okay, a Y configuration includes, let me look at this one. Okay, that takes care of the neutral. All right, delta configuration does not have, perfect. And how is 240 volts obtained from single primary phase transformer? Okay. You guys remember when those students came out to the field the other day? Those electrical engineering students?
Yeah.
They were all asking all of the same questions also. So if I'm able, I'm just going to throw out the question. Let's see what happens here. Not 100% if we discussed this before, but we're going to discuss it now. Okay, so here's my primary. And here's my secondary. All right, how many windings do I have on my primary side?
5.
No, how many not coils?
2.
Oh,
How many windings?
2.
How many?
Primary.
Primary. I got one set of windings, right? One coil. This goes to ground. Here's my complete path. So I have one coil and it's going in this direction. All right, that's the way it's wound. AC goes back and forth, but this is the direction it is wound. How many coils do I have in my secondary?
2.
2, okay? One is wound in this direction. The other is wound in this direction. I'll get 120 volts off of this side, 120 volts off of this side, and this is neutral, grounded. All right, the question reads, how is 240 volts obtained? So I'm going to have 240 volts from here to here in a single phase transformer. Why in this instance, and I'll give you this right here is fine as far as the winding direction. How am I able to get 240 volts from just one phase of primary? Think of the sine waves when you're looking at this. Is there anything unique? This is happening in an instant. And this is your sine wave. We got to draw a single phase here. All right. How many times does this happen per second? One sine wave?
60.
60.
60 times per second. So every 1/60th of a second, right, I have one sine wave. Does that make sense? If it happens 60 times per second, obviously one sine wave is one every 60th of a second. All right. It's not really happening in an instant, but it's enough to produce 240 volts. When I oppose my windings on the secondary side, two different directions, it's catching both what? This and this, very close to the same side. This is only 1/2. So every 1/20th of a second, I'm able to get both the peak and the valley very close to the same time. So I'm actually getting, because of the difference in direction here and here, I'm getting 120 and what?
160.
120, which equals 240. For us, as far as reading it on a digital meter or a analog voltmeter, it's going to read 240. Now it's not going to be exactly 240 because of the sine wave timing, but in 1/120th of a second, that's fast enough for it to go ahead and produce a voltage of 240 volts. So if I was to ask the question, how is 240 volts obtained from a single phase transformer? What in our windings gives us the capability to do that? The primary is in what direction? How many different directions? The primary is wound in how many different directions?
One direction.
One direction, okay. The secondary is wound in how many directions?
2.
Two directions, there you go. You can write that as the primary goes one direction and the secondary windings go opposing directions. They oppose each other. One goes one way, one goes the other. All right. Professor V, have I missed anything for today?
Y, you got Y delta, and you just hit the 240 obtained. Okay, I think that's all of it.
All right, so we're going to go over a little review here. I'm just going to go through the questions. I'm not looking for answers. One, this is insurance that you got the information you need. And two is to make sure we're both squares. Go square on the situation. How many times does one AC cycle produce no volts? We've done that. How many degrees are there in one full AC cycle? We've done that. At what degrees are voltage at their peaks? Done that. How many cycles there in 1 second? Done that. In one cycle, voltage is being produced all of the time. That's true or false. A load can be present whether it is energized or de-energized. That's true or false. The three types of load. Now we'll get into what we had today. The three types of load are, we know that, resistive, inductive, capacitive. A resistive load characteristics produce light and heat, and inductive loads characteristics are, it's a motor. A capacitive load is a capacitor. We know that. That's how we use them on our utility system. All right, so questions 11 and 12. You saw the video that was given earlier. When the guy was doing that video, he was including the full circuit. How many degrees did he say inductive loads were out of phase?
90 degrees.
90 degrees, okay. He was talking about what they call reactive power on a pure, and that's why I put capital letters, pure inductive load. How many degrees out of phase is it? Just the load itself, not the circuit.
180.
180, thank you very much. All right. Capacitors and capacitor banks are placed, well, you know the location. We did that with the college picture in the map. Power isn't available in three-phase some of the time, most of the time, all the time. That's what that question was. In both motor horsepower and transformer, kVA, well, that's what we talked about when we talked about the percentages of three-phase power. In a balanced three-phase system, the conductor needs 75% of what you need. The Y diagram is in what position? I provide a picture there so you can pick which one the Y diagram is. A Y configuration includes what is included in Y that's not included in delta. Neutral and ground.
Neutral ground.
Right. A delta configuration does not have
Neutral.
And ground. And how is 240 volts obtained from a single primary phase transformer? That's the question that you're going to see. And those are all multiple choice. All right, Professor V.
Yes.
Anything else we need to touch on here?
I think you hit on all the points there.
Okay. As a reminder, gentlemen, last Wednesday's video is part of this quiz.
Right.
So I'll produce the video for this one today. Don't forget to, and that's why I said quiz 4 part 1. That's the name of that video. And I'll put quiz 4 part 2 as the name for this one. So you can have those resources when you guys doing your quiz today. Okay. Yep. Somebody's outside.
Yep.
Any questions? Went over a lot today.
A lot.
Yep. And you really need to know these basics right here, what the load types are and what the configuration types are, because we're going to get, when we start getting deeper into three-phase, it's going to get, I have to admit, it's going to get a little bit more technically challenging. All right. Well, if I have, stop the share here. If we receive no other questions, or if you would like to ask a question once everybody has departed, you can do that. That's all I have for today. Now, who gave the safety meeting today? Keaton Miller. So who's part of mine? I do this today because I keep forgetting when we skip days. Good grief. X. I've got 12 windows up. Tools, attendance. So for my class, who's the last person to give a Javon, I know you did one, correct?
Yes, sir.
All right. Jonathan O'Brien, have you given a safety meeting?
No, sir.
Okay. Mr. Bell, you will be our Wednesday morning safety guy, okay?
Okay.
All right. Once again, I'm going to have somebody check the field today. If the field is soaking wet, you might have to be ready for tomorrow. If the field is still a swamp, as it was over the weekend, we might move to online tomorrow, let that thing dry out a little bit. From what Granger was telling me, it was all the way up. The whole field was covered.
Wow.
So we'll see how that drains off today. All right. Any other questions while we're all together? All right, gentlemen, have a good day today, and I will text you when all is available as far as videos and quiz openings. Dropping line.
Have a good day, sir.
You too, Scott.
Professor V,
Yo ho.
you told me to remind you for my resume
Yes.
today.
Sir. Yes, sir.
Just want to remind you.
Thank you. I appreciate it.
Thank you very much. See you later.
You look really smart with those glasses, man.
That's the only reason I wear them.
I hear you. I just don't wear them.
Have a good day, guys.
You too, Colin. What's up, Colin?
I was about to say, we only have 2 absences, right?
2 absences that you're allowed?
Yeah.
Yeah, that's correct.
All right. Thank you. All right. Have a good one, then.
You too, Trevon. James, rolling. Come on.
Wake up.
He's asleep.